Everyone. So, Unit 6 is really different because basically everything you've done up until this point has been about the derivative and its applications. So, in Unit 6, this is where we learn how to basically do everything we've been doing in reverse. So, let's go ahead and go through this list of topics that you'll need to know. So, the first thing you need to know is the idea of the accumulation of change. So, basically, we want to learn how to find the total amount. You can kind of think of it this way. If you're driving a car and you know your speed, you can use integration to help you find your total distance traveled. So from there, we move on to the Riemann sum and how to do left endpoint calculations, right endpoint calculations, and midpoint calculations. Those are going to help us approximate the area under the curve. And then from there, we learn definite integrals, which basically help us get the exact area. So Riemann sums are an approximation. The definite integral can give us an exact answer. So of course, from there, we're going to cover the properties of definite integrals, which are just going to make our calculations easier. And then we move on to what I would call the star of the show, the FTC, or the Fundamental Theorem of Calculus. There are two parts of it. Part one basically ties together those concepts of differentiation and integration. And then part two gives us a fast way to evaluate definite integrals, basically just using antiderivatives. So from there, of course, we're going to review how to actually do that. So how to find the antiderivative and also indefinite integrals. And then lastly, we're going to review techniques for antidifferentiation, which includes U substitution, long division, and also completing the square. All right, let's go ahead and jump into the first topic. Okay, so the first key idea that you need to know for Unit 6 is the idea of accumulation of change, which basically helps us calculate the total change in a function. So it's really the key idea for interpreting how to relate concepts like velocity and position. So let's just say we have v of t, which represents velocity. The area under the curve is going to represent the total change in position. It is important to remember your signs when you're going through this unit. So basically, if v of t is positive, the area is going to represent a positive change in position. If v of t is negative, the area is going to represent a negative change in position. Or you can think of that as movement in the positive or negative direction. So we're going to go into an example later that's going to explain this in more depth, but just a key note and key reminder here. Oftentimes, these questions are going to be signaled by keywords like total change, net change, total distance traveled, or something like that. It is important to remember that the integral gives you the total or net change in position, but you have to be careful if you're asked for the total distance traveled. In that case, you may need to take the absolute value of the velocity before you actually solve. So just a reminder to keep in mind the difference in distance and displacement. All right, let's go ahead and move on for now. So the next concept you'll need to know for Unit 6 is the idea of the Riemann sum, which helps us approximate or estimate the area under the curve. The good news is that at its core, it actually uses a very simple formula, which is just the formula for the area of the rectangle. So all you have to do is you have to find the width of each rectangle, which is going to be the same for all of the rectangles that you choose. Then you have to multiply it by the height. That I think is a little harder to kind of conceptualize, but really all you're doing is you're taking your x values, which are going to depend on whether you choose to do left hand, right hand, or midpoint approximation, and then you plug them into the function to get the height. So I did do a separate video on Riemann sums that goes into that in more depth, but for now, I'm going to leave it at that and go ahead and move on. I do want to talk about how Riemann sums relate to the definite integral. So basically, again, Riemann sums are an approximation, and the definite integral allows us to get the exact area. So again, I'm not going to go through this, but I do want to just kind of highlight this here. This is showing an example. So if we had the function x squared on the closed interval 0 to 2, A question might ask you to approximate the area, again, using Riemann sums. And then for part B, if it says calculate the exact area, that's when you're going to use the definite integral. All right, let's go ahead and move on. So the fundamental theorem of calculus really is kind of the bread and butter of Unit 6 because this is basically where we tie together two core concepts, differentiation, which we basically focus on in all of first semester, and integration, which is pretty much all we focus on in, I guess I should really say second half rather than second semester. So the FTC is broken up into two parts. We have part one, which is doing kind of what I already mentioned. It's basically showing you the relationship between integration and differentiation and demonstrating how they are inverse operations. So basically, if you get the area under the curve and then you take the derivative of that, you get the original function. So it's really just, again, showing you how they're inverses. Part two has to do with evaluating the definite integral. Basically, this is where we learn that we don't need to approximate the area using Riemann sums, and instead we can use the definite integral to get the exact area under the curve. So now quickly, let's talk about why the FTC is important for the AP exam or how it's related to the AP exam. For if you have to use part one of the FTC, you are usually going to be apply that by differentiating accumulation functions. So you're probably going to be given big f of x like this, and you need to know how to take the derivative of that and find f prime of x quickly, right? So again, it's that idea of undoing or performing the inverse operation. And then for part two of the FTC, these questions usually involve finding the antiderivative and then applying the limits of integration. So basically just evaluating definite integrals. All right, let's go ahead and move on. So the next thing you're going to need to know is how to find antiderivatives and indefinite integrals, and basically just their rules and notation for doing so. So as a quick refresher, let's go over some terminology. Basically, when you find the antiderivative, you're doing the reverse of taking the derivative. An indefinite integral is basically the family of all of those answers that you could get. So I'll do a separate video going more in depth on that, but kind of the key takeaway that I want you to have right now as a quick refresher is that after you take the integral, like in this example here, you have to add plus c onto your answer because again, it represents the family of all possible functions. Okay, so let's just go through these quickly. Here is a list of the basic rules and notation that you'll need to know. The power rule here, this is very common. Definitely memorize that and be really sharp with it. You've already seen these kind of above when we went over some of the definite integral rules, so I'm going to kind of skip through that. That's just the constant rule and the sum and difference rule. And then here is another list of integrals that you may see, and I highly recommend that you have these memorized and are super sharp and quick with them. So I'm not going to go over those in depth now, but you can just see my list here, and this will be available for download. You can check out the description box for more info. And now finally, for Unit 6, you will have to know 3 techniques of integration. The first being U substitution. I will do separate videos that go more in depth on each one of these, but for now, here is a quick overview of the steps. Basically, first you let U equal g of x, which is usually the inner function. Then you're going to take the derivative of u, then you rewrite the integral in terms of u, then you evaluate the integral with respect to u, and finally you substitute back for basically g of x for u in the result. All right, the second technique you'll need to know is the technique of long division. So you're going to use this when you have rational functions, which as a refresher they basically look like a fraction. So here you would want to actually do long division first and then integrate. And then finally, the third technique you have to know is completing the square. So as a refresher from really like algebra 2, completing the square is a method of factoring that you can use. So sometimes if you are given something like this with a quadratic, you want to actually complete the square first. Sometimes then you'll have to incorporate U substitution, and then you want to integrate after that. All right, thanks so much for watching. I'll see you in the next one.